Thanks. So today it would be on things related to flag complexes. Oh. So I'll start off with some definitions. So as usual, K would be a simplicial complex on M vertices. And we say that K is flag complex. There's different ways to characterize this. They're all the same. One way is if the minimal missing faces are all edges. I'll give an example in a minute. Equivalently, if you have any set of vertices that are pairwise connected by edges, so that means you have a bunch of vertices and you have an edge between every possible two vertices. In this case, any set of vertices spans a simplex. So if you have a bunch of vertices and there's edges between every two possible vertices, then you fill in all two faces, you fill in all three faces, and so on. So for example, something like boundary of a triangle is not a flag complex because there's a missing face here, which is a two-face, but you're only allowed to have missing faces, minimal missing faces that are edges. But if you look at a square, or the boundary of a square, that is flag. There's no missing two faces, but there are two missing edges. If you're to look at, my drawing is not great, but I'll see what I can do. If you were to look at something like this, you've got a missing two face here, a missing two face over here, so this is definitely not flag. But if you filled in those two missing two faces, then what is missing is there's an edge missing, and that's the one minimal missing face. So this is flag. Okay. One more definition. Given a simplicial complex, say K, then you can look at flagifying it. So the flagification of K is the minimal flag complex on the same vertices as K, and it contains K. Right, so in this case, if I label this A and I label this B, You started out with a simplicial complex that was not flag. You added some missing two faces to get something that was flag, right? So this would be the flagification of this guy. All right, so that's...
So K is completely determined by its one skeleton?
A flag complex is completely determined by its one skeleton, yes. Okay, but so it is missing the triangle. So if I label these 1, 2, 3, 4, it's not missing, sorry, it is missing triangle 1, 2, 3, but it's missing that because it's missing 1, 3, right? So there's something smaller than the triangle 1, 2, 3 that's missing. The edge 1, 3 is missing, right? So, and you're looking at sort of the minimal missing faces.
Okay, so missing means missing from big complex and minimal.
Yes, yeah. Any other questions? Okay. Flag complexes are used ubiquitously. So they're a very special class of simplicial complexes. They show up in metric spaces or topological data analysis, where they're Vietoris-Rips complexes. They show up in graph theory, where they're clique complexes. They show up in geometric group theory, which we'll talk about a little bit towards the end, and I'm sure they show up in lots of other places as well. Right, somehow they're a very user-friendly collection of simplicial complexes. So we want to consider polyhedral products, simplicial complexes, and flag complexes in particular, and see if we can say anything. So let's do a little bit of homotopy theory. And at this point, the simplicial complex won't have to be flag. Just work it for any simplicial complex. Yesterday, we saw that working one vertex at a time, there was a push out where you had a link of some vertex, including it to the star. Including it to the restriction, and you push out to get K. And this star was the same thing as a link joined with the vertex V. Well, there's a nice push out map that you can get from this. Along the top, you've got the link including into the join of itself with a vertex. So you could, on the bottom, take this restriction and include it into itself joined with the same vertex. And along this side, include the link into the restriction and join everything with the vertex. And you have a nice commutative diagram, so there's a push-out map. And what does that do for you in in the world of polyhedral products. It's easier to think about yesterday we were concerned about turning this into a push-out and then using push-out properties. Today we're going to take the opposite tack. We will use the fact that this produces a push-out, but instead of considering co-fibrations connected to that, we'll consider fibrations connected to it. All right, so to do this, I need a lemma. This is the cube lemma. Right, so this is due to Mather. And it says, suppose there is a homotopy commutative cube. Suppose you have a homotopy commutative cube where the bottom face is a homotopy pushout. And the four sides are homotopy pullbacks. There's a technical thing with the cube lemma I don't really want to get into, but if you want to press me about it, I will talk about it. Suppose you have all of this data, then the conclusion is supposed to be that the top face is also a homotopy pushout. All right, well, let's see this in action. I think I've got enough space. We need a homotopy pushout to start with as a bottom face. Well, we've got one because we saw yesterday that this pushout of simplicial complexes produces a pushout of polyhedral products. So we have, in complete generality, it works for any xak. It just takes time to write down. All right, this will be the bottom face. And to produce the pullbacks on the four sides, we're going to take the conon AA for K and map it into the conon AA for this complex. There's a join here, so that will break up as a product of polyhedral products. And I didn't leave myself a whole lot of room. So you'll have an XA for the restriction, and then the polyhedral product for that single vertex would be just a copy of X. Map all four corners into this and take fibers. Right, so fiber from XAK into this is some mysterious space F. The fiber from the restriction cross A into the restriction cross V, well, this is going in by the identity map on the restriction and the inclusion of A into X. So its fiber, the restrictions will cancel out, and you'll just be left with a fiber, I'll call it YV, where now I have to run back and forth between blackboards. So YV is the homotopy fiber of the inclusion of AV into XV. If I go in from this side, I've got a polyhedral product for a link cross X, mapping into the polyhedral product for the restriction cross X. It'll map by a product, which is the identity on X, so that cancels out when I take the fiber, leaving just the fiber from the link into the restriction. So I'll call that G. So there was a pullback on the front side and on the right side. Mapping this corner in, you've got the link mapping to the restriction and A mapping into X. So when you take fibers, you'll get a G crossed with a Y. And if you play around a little bit, you'll see that these are both projections. And whenever you have sort of a general thing, whenever you've got, what's letters I haven't used yet, if you have a B cross a C, and you project to B and project to C, then its push out, homotopy push out, is a join. So I'll write that as suspension B smash C. So F here is G, suspension of G smash Y. All right, so stop and think about what we've done here. The important part was this vibration. All right, so we've got a vibration where the space we care about is in the middle, and it maps down to kind of smaller spaces in some sense. Polyhedral product for the restriction cross X, and the fiber you can identify as this suspension of G smash Y. And you get more because if you think about this composition again, if you just restrict to the polyhedral product for the restriction, that maps, it includes into this factor, right? So this factor has an inverse. On this side, the X mapping in maps out identically to the X, so that has an inverse. So both of the individual factors here retract off this. If you could multiply them together, the whole thing would retract off. This is not necessarily an H space, so you can't do that, but you can after you loop. and then I would split the fibration. So loop of the polyhedral product is the loop of the polyhedral product for the restriction across the loop on the component coming from the vertex V, across the loop on the suspension of G smash Y. Think about what this says. This polyhedral product is the thing we care about. We've written its loop space in terms of a polyhedral product on a smaller number of vertices, an ingredient space. The Y comes from the ingredient space. The G comes from polyhedral products with fewer vertices. So all the information on this side has to do with polyhedral products with a fewer number of vertices than on this side. So in some sense, you've kind of simplified the problem, and you've set yourself up to do an induction on the number of vertices, because you could iterate on this guy. The only tricky part is trying to identify, in particular, this fiber from the link into the restriction. In some sense, this is kind of dual to the things that we were talking about yesterday. So yesterday we had this the link star diagram was giving this push out of polyhedral products, and from it we were getting interesting co-fibrations and splittings. And here we're using that to get interesting fibrations. So this will give, in particular, homotopy group information, because the loop space just shifts the homotopy groups down by 1. Okay. Is there any questions to this point?
Vibration in the middle and the vibration in the middle, is that sort of a generalization of Guinea's vibration?
Yeah, in a way.
I mean, you're sort of getting a join into what might be like a wedge into a product, and maybe that's...
It's slightly different, I think, in the sense that he would be looking at, so Guinea's vibration would, if you just think of it as X wedge Y mapping into X cross Y.
Right.
Right? In terms of polyhedral products, you're looking at a simplicial complex with just two vertices mapping into one foot with an edge.
Right.
Right? And this is slightly different because you have a K going to a restriction joined with something else.
Right, but in the case of 2 points, that edge, if you remove it, you're getting that X upper A upper K would be, so it's exactly the same in that
Fair
example.
enough. Yes, you're right.
Okay, thank you.
Okay. So I say this is really something that goes back to Felix and Theriault. They produced this vibration. They didn't quite state it this, but then they sort of went into rational homotopy theory and how this vibration says some interesting things. Okay. Just as an example, to ground things a little bit, let's think of the moment angle complex. All right. So what is this saying if we put it in this context? So the interesting bit is here. So the homotopy fiber of the A into the X, which in this case would be the homotopy fiber of the circle into the disk. And that'll be just a copy of the circle. So in this case, the loop on, say, K would be the loop on the restriction cross. Now, the x's in this case are going to be d's, and they're contractible. So this term is going to vanish. And then we'll have this slightly mysterious space G. We'll have a suspension, and then we'll smash it with a circle. So that's a double suspension. So if you could understand what these fibers are from links into restrictions, you would understand this whole thing. That, by the way, as I've learned over years, is the whole business. If you could understand links into restrictions, you've got everything. And you walk away and declare victory. Okay. All of this business turns out to be natural with respect to simplicial inclusions. So the vibration and splitting these are natural with respect to simplicial inclusions. Right, so this is non-trivial, by the way. It just doesn't come for free. You have to work a bit to get that. But to see this in example, so let's specialize a bit. Let's look at pairs of the form x comma star instead of x comma a, just because the point's easier to deal with. What else did I want to? Think about L is another simplicial complex, and we'll let it be the vertex set of K. So it's just m disjoint points. And there's a simplicial inclusion from L into K, just by including the vertices. Let's see. There's a particular vertex that we're focused on. Let's just make it concrete by making it vertex M. And in terms of this homotopy fiber of an A into an X, now our A is a point. So YM is the homotopy fiber of a point into XM. So that's just the loops on XM. All right. So the naturality property says, one more thing. For L, if we look at x comma star for L is just M disjoint points. So this polyhedral product is just going to be the wedge of all of the xi's. So if when we look at the naturality statement, we'll have the loop on the x comma star polyhedral product for K. Mapping into that will be the loop of the x comma star polyhedral product for L, and that's a wedge. Each breaks up as a product. The x comma star case, you have a loop on a polyhedral product for the restriction, cross the loop on an x, M, because our vertex is M, and then a loop on the suspension of G, smashed with the y in this case is a loop XM. On the other hand, for the disjoint point case, the restriction is you restrict away, you've got M disjoint points and you just discard the mth one. So you still have M minus 1 disjoint points. You'll get this copy of loop XM. You'll get a G with respect to the disjoint point case. And the maps here, if I call this one F, just to give it a name, this will be a product that will look like some map of restrictions called G. You'll have an identity on the loop XM. And on this part, you'll have the loop of some map of G's suspended, smashed with the identity on loop XM. All right, so what?
Steve, could we say that for
This one?
yeah, thanks.
Okay. All right. Maybe back up. Let's recap. This started as something about flag complexes. I gave a definition of a flag complex, and then I completely forgot about flag complexes and started talking about any simplicial complex, produced some decomposition, said it was natural, restricted to some weird case where you're looking at the vertices mapping into a full complex, right? You get a crazy picture like this, right? Where am I going? Okay. So a little bit of intuition. Loops on wedges are nice. They're really well understood, okay? In particular, if each of these xi's was a suspension, then there's a Hilton-Milner theorem. And that says the loop on a wedge of suspensions breaks up as a big product of loops on iterated smashes of the ingredient spaces. Okay? And it tells you that all of the maps coming in to this loop on a wedge are loops on Whitehead products. Okay? If you don't care about the fact that these are suspensions, there's an analogous result due to Porter that will break up the loop of a wedge. And again, it sort of describes the incoming maps have all got to do with loops on Whitehead products. All right, so there's Hilton-Milner and this result of Porter are saying something kind of interesting. Now, when you think about these polyhedral products, if you've got a missing edge, that corresponds to a Whitehead product. If you've got a missing two-face, that corresponds to a higher Whitehead product, whatever that is. A missing three-face is an even higher Whitehead product. Okay? So loop on a wedge has got lots to do with missing edges, as you might think, because it's all disjoint points, and it's all phrased in terms of Whitehead products. If you have a flag complex, its minimal missing faces are all edges, right? So there's no missing two-face, there's no missing three-face, there's none of this higher Whitehead product stuff. It's all happening at the level of Whitehead products. So the intuition might be that what's kind of happening is you're taking the Whitehead product information here, and you're collapsing some of it out corresponding to the edges that you're putting into your flag complex, right? And any possibility of a higher Whitehead product that might be showing up, that would have corresponded to a greater missing face, but the flag conditions means you close all of them off, right? So this map, as a guess, might have an inverse, right? So the intuition suggests that this map F has a right, I'll say, homotopy inverse. If K is flag. And in fact, that's true. So this is something that Terrace and I did. So if you have a flag complex, this map has an inverse. And you can generalize that to some other polyhedral products, but I'm just going to focus on moment angle complexes because they're the ones that everybody gets excited about. Right? So as an example, if K is flag, then if you look at the moment angle complex corresponding to the vertices of K, mapping into the moment angle complex for K, loop that, this has a right homotopy inverse.
The example on your intuition had to do with x comma point, but the moment angle sort of angle comma so reverses, like point comma.
Right, okay. So I said there was a statement in between these. It says it works for some other polyhedral products.
Oh, okay.
And the way you would see it for something like the moment angle complex is you would say, well, go down to djk, that's CP infinity comma point. That applies, right? And now look at the fibration where you take dj into the product of CP infinities with the fiber, the loop ZKs. Yeah. Any other questions? Okay. This says something kind of interesting. So as a consequence, polyhedral product for M disjoint points, its moment angle complex, that's known. It's known to be a wedge of spheres. So its loop space, the Hilton-Milner theorem would tell you that that's a product of loops on spheres. And now the loop of the moment angle complex for this flag complex retracts off something that's homotopy equivalent to a product of loops on spheres. So it too would have to be a product of loops on spheres, or possibly a sphere. If you think of like loop S2 as S1 cross loop S3, you might be picking off one of the spheres. So in some sense, if you have a flag complex and you look at its moment angle complex, you can figure out what its homotopy groups are. If you could enumerate what these spheres were, then you could look up at the tables of homotopy groups of spheres and feed them into what the homotopy groups of the moment angle complex is. Right? So Martin's talk, for example, talked about things like the homology and cohomology of polyhedral products, right? You also want to know things about their homotopy groups. And this is getting some information, at least in special cases of flag complexes, right? So a little bit like the talk yesterday, maybe you've got statements that don't work for all simplicial complexes, but there are nice families for which you can pull out more information. Okay. Right. There's some other things that have come out of this. So Lewis generalized this and showed that if you've got, if now K is a K skeleton. Mm-hmm.
That map, the map down there, that has the right homotopy inverse. What can you say about that map? What detects it? It's an essential map.
It's an inverse, yes. So it's.
So that means that some of the spheres on the right appear on the left.
Yes. So the way you think of it. So this.
Yeah.
This is a product of loops on spheres. They are all indecomposable, except for special cases like loop S2, which is an S1 cross loop S7, right? So if you're going to retract something off this, it will peel off some of those indecomposable pieces, but not other ones.
Thanks.
Okay. Right. So Lewis Stanton recently showed that if K is the K skeleton, too many Ks, then it is also a product of spheres and loops on spheres. No, flag K, sorry, of. Sorry. Yeah. Then this is a product of spheres and loops on spheres. And in particular, this would say that if you had a graph and you thought of it as the one skeleton of its flagification, then you could apply this theorem to show that the moment angle complex corresponding to the loops on, sorry, the loop of the moment angle complex for that graph broke up as a product of spheres and loops on spheres. And sort of getting to Martin and Tony's question, you could say, well, which spheres are, when you do this retraction, which spheres are you catching, right? Can you enumerate the spheres that map into loop ZK and those that are in the complement? And Terrace's student, Fedor Villajanin, did this. So he enumerates the spheres. In this case of a flag complex. So you get complete information.
So for example, K is a barycentric subdivision of a triangulation of two origin and all that. When it's flat, it's a barycentric subdivision. And the loop is torsion disappears. So all the torsion is away and a barycentric subdivision basically.
Yeah, looping destroys a lot of information, surprisingly. Yeah. So as another example, if you look at the boundary of a pentagon, right, then McGavran tells you that the moment angle complex corresponding to the it is some connected sum of sphere products of two spheres. But after you loop, you only see loops on products of spheres. So that connected sum information is sort of vanished somehow.
Can you still see, sorry, can you still see that information in the Whitehead products? Like, could you see torsion? The fact that the original moment angle complex had torsion, can you see that in the Whitehead products of the, I mean, yeah, I mean, not the Whitehead products, but the Pointeroggan products, the product structure in the loop space?
Well, the loop space it's because the loop space is a product of spheres and loops on spheres, as a module anyway, there is no torsion, right? Now, the multiplication might still be quite complicated, and the decomposition is not telling it to you because it's only a decomposition of spaces, not H spaces. So, I mean, there might be something that kind of remembers the torsion, but I'm not sure what. Mm-hmm. Right. Yeah.
I mean, there's got to be something there, because if you take that into the bar construction, because James and Luke could use bits and K back. I think Luke could use the bar construction. And so the ring structure has got to remember the torsion.
Right, okay.
Get into the bar construction.
Okay.
If you need, right, I mean, you have to pick up the thing, right, exactly. But it's there somehow. It can be reproduced.
Right, so this is flag complexes is giving you sort of interesting homotopy theoretical information about certain polyhedral products. Okay, so I don't know if this next part is connected to the first part or disjoint from it, but anyway, it's both about flag complexes. Let's look at a little geometric group theory. Now, I don't know any geometric group theory, so I'm a bit of a charlatan up here. But I can give some definitions and some facts. So let's let gamma be a graph on M vertices. And let's, to each vertex, assign a group. Then the graph product G sub gamma, G super gamma is following. Do you still want me to keep this one, Tony?
Okay, go ahead.
Here, I'll write on this board because I don't have much time left. Start with the free group on all the copies of G and introduce some relations where if there's an edge ij in the graph, then take any elements in gi and gj and make them commute. That's the graph product. So for example, there's two special cases. If gi is a copy of the integers for every I, and let gi be the generator, then the right-angled Artin group corresponding to this graph is just the graph product where you take free product of m copies of Z, and then you do the commutativity relations, which can be given just in terms of each generator of Z. Right, so start with a free product. Whenever you see an edge, let things commute. And there's a right-angled Coxeter group. Where you start with, instead of Z's, Z mod 2's. And the same commutativity relation. The geometric group theorists love these groups. So here's an interesting property or two. When you think of the graph product, so you've got this join, and then it projects down to the graph product, and you could map this out to the product of all the G's. Right? So this is like the free part, and in some sense the abelian part, if this was like all Z's, for example, and the graph product is in between. And this is analogous to everything we've been thinking about in terms of polyhedral products. Right? So groups, when you look at group theory, you don't look at the group itself. If you want to apply topology to say something about group theory, you would look at its classifying space, which is a k pi 1, where the pi is the group, right? So we should phrase this in terms of classifying spaces of groups. Right? So this should look like a product of the BGs. The free part for spaces it looks like a wedge. And in between, you're going to have a polyhedral product. I could write gamma, but I'm going to write something a little bit what the geometric group theorists do. K will be the flagification of gamma.
Excuse me, Stephen, you're considering them as discrete groups.
Yes, yeah, more than anything. Yeah. All right, so this construction of graph products coming from geometric group theory is sort of, it looks a lot like certain polyhedral products. Okay? So concretely, so this is due to Panov and Vertex. If you've got simplicial complex K, not necessarily flag, and if you look at a sort of graph product associated to it, sorry, what am I? Look at the polyhedral product associated to it. Take its fundamental group. You get the graph product of the one skeleton of K. I'm still writing, okay. One skeleton. And the more interesting one, if K is flag, then this polyhedral product is acyclic. So in other words, it has a non-trivial pi 1, but all its other homotopy groups are 0. So it's an Eilenberg-MacLane space. I shouldn't erase that one.
There's a question. What is G to the K?
This is a G to the K1.
G to the K1.
Take the one skeleton of K. Yeah, okay.
But this part is classical, right? It's not really, and that goes back
That
to
was proved by I think the first
It's
proof
Whitehead,
was by Mentor
Whitehead. It's Whitehead way
Whitehead.
of constructing acyclic spaces from the graph, yeah.
Okay.
That's, yeah. There was some other case about the commutator product, which, yeah.
Better?
Part B is different only. If it's not flag, it's definitely not a K flag.
Yeah, okay.
Mentor stuff, but if it only for a student.
The interesting thing about this is because this is an Eilenberg-MacLane space, it says that this polyhedral product is classifying space for the graph product of G. Right? So in particular, if you look at a classifying space for the right-angled Artin group, then all of the groups are Zs. Their classifying spaces are circles. So the polyhedral product S1 comma star, this is a model for the classifying space of this right-angled Artin group. And for the right-angled commutator group, all the groups are Z mod 2. Their classifying space is RP infinity. So you get a very nice model for the classifying space of a group that the geometric group theorists are incredibly interested in. They've used this to great effect in geometric group theory, right? So the question I will leave you with is, here's some really nice groups running around, right? These graph products of groups modeled, their classifying spaces are modeled by interesting polyhedral products involving flag complexes. We know interesting information about the homotopy theory of these guys. What else can we say about it? Right? There's a nice link there between two different subjects, which is kind of only beginning to be explored. What else can be done? I'll just leave it as an open question. I don't know. I leave that to you. So, thank you.